Hi, welcome to R2E. So in this video, or probably in the upcoming videos too, I will be talking about a topic that is called as, okay, let me use a bigger size, pen size. So we will be talking about time independent perturbation theory. So we will be talking about time independent perturbation theory, and so in principle, well, this is actually a course apart from the course from advanced quantum mechanics or quantum mechanics 2, and I haven't discussed in any of my series or in any of my videos much on quantum mechanics 1 course, that is linear algebra and most of linear algebra, and linking that to quantum systems and how to solve for certain models. But I assume that anyone who's watching this video have some sort of a knowledge of quantum mechanics 1, and we will try to build on it. Okay, so one of the central ideas that one learns in quantum mechanics 1 is that you have models, you have certain Hamiltonians H, for which you can solve this eigenvalue problem exactly, right? You can solve this eigenvalue equation and you get the solution for En0 and this eigenkets. Now the point is, there are very limited number of models that can be exactly solved. So few of them that you might have learned is particle in infinite well, particle in well probably, the simple harmonic oscillator, the hydrogen atom problem, and a couple of more. But these forms the central idea of all the solvable models that we have. But these models are except for hydrogen atom, these models are very simplified limit of the reality. But the question is, how do we solve systems that are in principle not so simple but are more realistic and hence have more complexity. So obviously it's not possible sometimes in general to find solution to such problems exactly, but the idea of perturbation theory is to link these already existing solutions to solution of the problem that you can't exactly solve. So to formulate what I'm trying to say is, suppose you have systems something like this. So this is your Hamiltonian and it acts on an eigenstate, and then you have En and you get your eigenstate back. Now the problem here is that you know the solution, so you know the solution to this part of the problem, that is EH something like this. Now the idea of perturbation theory is to use this set of eigenvectors and eigenvalues to actually arrive at the set of n and En. Now to tell you that this set is not a solution, is not a solution, okay, let me put a cross here, not a solution to h plus lambda v problem, but in principle it is very close to that solution, or yes, in principle it is close. So it is close to the solution, and how close, it depends upon the strength of lambda, that how powerful your perturbation is. You realize that you get more and more closer to the real solution. So sometimes it might happen that your lambda is so weak that you don't even need to consider the perturbation, but when your lambda is, let's say, some intermediately strong, then you probably have to consider few terms, and you can leave the rest of the terms. To illustrate what I'm exactly talking about, I will consider a model that is exactly solvable. So I will consider this model two-level system. So consider you have two levels in which you have the eigenenergies as epsilon 1 and epsilon 2, and then you have your off diagonal elements, and these off diagonal elements, let's say, are given by lambda v. For the most generalized solution, for the most generalized problem, I'm supposed to put a star here and a star here, and then now because of the hermiticity, this does not have to be the conjugate of it. Sorry, this has to be conjugate of it. I'm sorry. So this has to be conjugate of this thing because of the hermiticity of the Hamiltonian. But I will not tackle with this problem per se, but I will do a relatively not so easier but a similar problem on the level of difficulty, I would say. That is when lambda and v are real. Not much of a difference comes from it, but if someone wants, you can try to solve this problem exactly, and you will realize that both the results from this problem and this problem, they're kind of the same. So for the illustration purpose, I will try to solve this problem, and I will try to make the point of the perturbation theory, why we are using perturbation theory, and how it makes sense to use perturbation theory. So the first thing is to compute its eigenvalues. For that, I will do is determinant of h minus of e times identity, it should be 0. So in principle, epsilon 1 minus of e lambda v epsilon 2 minus of e. So this thing should be 0. So this implies that epsilon 1 minus of e epsilon 2 minus of e minus of lambda squared v squared should be 0, and this implies that e squared minus of epsilon 1 plus epsilon 2 times e plus epsilon 1 epsilon 2 minus of lambda squared v should be equal to 0. Now we can simply use the quadratic formula, the formula for the quadratic equations. So e plus minus is equal to epsilon 1 plus epsilon 2 divided by 2 plus minus epsilon 1 plus epsilon 2 whole square minus of 4 epsilon 1 epsilon 2 minus of lambda squared, v squared, power 1 by 2, power 1 by 2, and again divided by 2. So this becomes epsilon 1 plus epsilon 2 divided by 2 plus minus, and okay, let's do it in detail. Epsilon 1 epsilon 2 whole squared plus 2 epsilon 1 epsilon 2 minus of 4 epsilon 1 epsilon 2 plus 4 lambda squared v squared 1 by 2. There's again 1 by 2 here, and if you look carefully enough, so what I'll be left with is here is plus minus 1 by 2 epsilon 1 minus of epsilon 2's whole squared, because there will be negative here and you will get a whole square here, plus 4 lambda squared v squared to power 1 by 2. Great. Now let's bring this quantity epsilon 1 minus epsilon 2 outside of the brackets. So that will be epsilon 1 epsilon 2 plus minus 1 by 2. This will be epsilon 1 minus epsilon 2, and there will be 1 plus 4 lambda squared v squared upon epsilon 1 minus epsilon 2 whole squared to power 1 by 2. Great. So now let's analyze this solution, okay, in some limits, right? So say lambda equal to 0. Now for lambda equal to 0, the solution with E plus minus would be epsilon 1 plus epsilon 2 divided by 2 plus epsilon 1 by 2 plus epsilon 2, sorry, minus of epsilon 2. And which is equal to epsilon 1. And similarly here epsilon 1 plus epsilon 2 divided by 2 minus of epsilon 1 by 2 plus epsilon 2 by 2, and that will be epsilon 2. Great. So you realize that in the limit that lambda is 0, your eigenvalues of the Hamiltonian doesn't change. But for some finite value of lambda, obviously they will change, and how they change, let's try to look at. So here this term is actually of the sort is square root of 1 plus x. So let's do the Taylor expansion. So first term will be 1, and then we will have plus f dash of, sorry, Maclaurin series, f dash of 0 times x plus 1 upon 2 factorial f double dash of 0 times x squared plus order x to the 3 terms, right? So let's compute. So f dash of x is 1 upon 2, 1 upon square root of 1 plus x, and f double dash of x is 1 by 2, and there is minus of 1 by 2, and there is 1 plus x to whole cube. Now let's put it in the series back. So we have the series as 1 plus x by 2, and then we have minus of 1 by 8 x squared plus order x cube terms. Great. So now let's plug this thing over here. So E plus minus equal to epsilon 1 plus epsilon 2 divided by 2 plus minus epsilon 1 minus epsilon 2 divided by 2, and then there is 1 plus, so x by 2 is okay, so this is so this will be 2 lambda squared v squared upon epsilon 1 minus epsilon 2 whole squared, and then you have second order term, so that will be and divided by 8. So okay, let's do it properly. So that will be 16 lambda to the 4 v to the 4 epsilon 1 minus epsilon 2 to the power 4, and there is 1 upon 8. I hope I'm correct. Oh, and this is a negative. Yes, and this is a negative. Great. And there will be plus terms. Okay, so let's now analyze the corrections to the solution. So we saw that when lambda is 0, so when lambda is 0, so let's check the corrections too. So when we have, okay, we have epsilon 1 0 and epsilon 2 0 are basically just epsilon 1 and epsilon 2. We saw that earlier. Now for epsilon 1 to the second order correction, it is equal to, so if you do this thing, so that will be epsilon 1 plus, so if you go up there, okay, so if this term goes here, 2 cancels, this term and this term cancels, you are left with lambda squared v squared upon epsilon 1 minus epsilon 2, and for the second term you are left with epsilon 2, and then you have a negative sign, and that is lambda squared v squared upon epsilon 1 minus epsilon 2. Okay, So this is good, and similarly you can check for a fourth order correction. Now obviously, so first, so let me put in some exercise here, and then we will try to analyze it a little better. Exercise is get correction of epsilon 4 and epsilon 6, right? So repeat the analysis, add one more term here, x cube term also, and then you will get a correction epsilon 4 and epsilon 6. And another exercise I want you to do is get no is it's relatively more important, I would say. Show that there are no odd corrections to epsilon 1 and 2. Okay, so how do you show that? So let me give you a hint here. So instead of considering the expansion of 1 plus x, use 1 plus x squared. I think yes, 1 plus x squared, and do its Taylor expansion, and then you will realize that you still only get the even terms, you don't get the odd terms, and then you can say that okay, there are no odd corrections to this Hamiltonian, to this energy Hamiltonian. Okay, great. So these two problems, they make sense here. So now let's try to analyze the solutions that we have got again. So obviously, so depending upon the strength of lambda, you will realize that how many terms you need to keep, and obviously how strong is your perturbation, it will decide how many terms you need to keep. So if there is no perturbation, then the energies are same. But if there is little perturbation, and you have to consider, obviously there is no first order effect, there is only second order effect, so you need to consider this kind of term here. Okay, and if there is more perturbation, then you have to also consider the fourth order term. So depending upon the necessity and depending upon the strength of V, you have to consider higher and higher order perturbation. Here I will not give a example, or we will not quantify that how much is the strength of V and how many orders that we need to consider. Is that when your V becomes strong enough that your perturbation is no longer working. When I say no longer working, is that the correction that you have given using this Taylor expansion, it's not good enough. Either it is, because here you can see that suppose your perturbation is strong enough that you have to also consider a fourth order term, but if you are using corrections only up to the second order, it will be overshoot. So your real solution probably will be something, your perturbed solution would be something like this, or your real solution, that is your experiment or numerical diagonalization, numerical techniques, or numerically solving your differential equation would be something like this. So there will be some difference here, and but if this difference is minuscule, that is dependent upon how strong this term over here is. But we will not determine how strong we need to be for now for us to consider higher and higher order terms. Okay, so this is, I think, nice, and this gives a nice idea of what exactly in perturbation we are doing. So in perturbation, what we are doing is we know the solution. So in principle, okay, so in this case we can actually diagonalize the whole problem, but here what we did was we used the diagonal solutions, these solutions epsilon 1 and epsilon 2, and we added different added lambda 1 and lambda 2 such that we get to a solution when system is not diagonal, but it has some off diagonal terms also. Now similar analysis could be done when we have systems that are of infinite, that lie in infinite Hilbert space, We will do that later, but before that, obviously, we have to formally develop the formalism of how do we going to tackle such problems. This is not a formalism, this is a introduction, and this is an example of how perturbation is acting and what exactly are we expecting from perturbation. Okay, so there's one more little thing that I would like to talk about is when perturbation works. So let's look at it. So we had our e plus minus as epsilon 1 plus epsilon 2 divided by 2, and then we had plus minus epsilon 1 minus epsilon 2 divided by 2, and then we have 1 plus okay, I have to, where was the solution? Yeah, 4 lambda squared v squared epsilon 1 minus epsilon 2 whole squared to power 1 by 2. Now, till when this will work is that now here I will assume that your lambda, it's complex, and because we want to talk about the convergence of the solution. So in principle, so why I'm talking about convergence of the solution is, so in principle, if you consider all the orders of this correction here, if you use all the infinite orders of this correction in perturbation in power of lambda, they should converge. They should converge to a real solution. They should converge to the real solution of the problem that you might get from numerical diagonalization. You won't have an analytical solution for that, or numerically solving the differential equation. So, but obviously, so whether it will converge to that or not, it depends on lambda. So let's take a look at here. So for lambda to be complex, so I could have so this part could go to 0, and that would be something like iota. So okay, wait. So that could be 1 plus 4 lambda squared v squared upon epsilon 1 minus of epsilon 2 whole squared equal to 0. So this implies that you have you have minus square root of minus 1, that is 2 lambda v epsilon 1 minus epsilon 2, this is equal to iota equal to 2 lambda v epsilon 1 minus epsilon 2. So iota epsilon 1 epsilon 2 equal to 2 lambda v, and say I set lambda to be 1 here because I have the freedom to do that. So iota epsilon 1 epsilon 2 equal to upon 2v equal to lambda. So and you realize for lambda equal to this value, so for lambda equal to this value, this is a branch point. This is a branch point in a complex plane. So this is a branch point in a complex plane because it is more of like a square root of z kind of function. So it's a branch point, and hence there is no convergence. So if you look at it, so when your v is comparable to epsilon 1 minus epsilon 2, or in some sense your lambda goes to 1, or it is exactly 1, so the solution doesn't converge in that sense. But and this could be, and this is a nice example of how complex analysis give the idea into convergence of the solutions, and probably we will discuss it more in detail later on. And yes, and we will discuss formalism probably in the next part, and then we will take up some examples of how to use time independent perturbation theory for different kind of systems. Okay, see you in the next video.